Thank you. Yes, I'm Arjen. This is joint work with my colleagues from Delft, especially Casper Bach-Paulsen and Robert Krabbers, who are also here at POPL. And this is work on defining semantics for new languages in such a way that their definition, the specification, is type-safe and executable by construction. And the way that we like to do this is using these intrinsically typed definitional interpreters. If you've never seen that, I'll show you the kind of prototypical example of this, which is the simply typed ladder calculus. I'll show a fragment. So what you do is you embed the syntax of the well-typed expressions in your language into Arcta in this case, using one of these index type families. And then you kind of merge the syntax rules with the typing rules to get these constructor typings. And the nice thing about doing it this way is that you can define these evaluation functions whose signature expresses type preservation. And this has several benefits. So for one, I don't have to deal with any partiality that you might encounter in an untyped interpreter due to a violation of type preservation. And at the same time, this type preservation is now enforced interactively, which means that I'm never surprised when I later would write a proof, because I don't write a proof later, I write it as I write the specification of the semantics. And we think this is a nice format. You get these executable and type-safe specifications. They're also quite concise. They're understandable, as Adam also claimed this morning. And they're maintainable, because you don't have this separation between the proof world and the semantics. Now it's kind of folklore to do this for these simply typed languages, and we have previous work on extending this to ML references and non-lexical binding. But this work is on extending it to these session type languages. And there are two features in those languages that kind of make this interesting, linearity and the concurrency and cross-thread communication. But in this talk, I will focus on the linearity aspect. So what is the role of linearity, and how does it get in the way? So let's look at a small session-typed program and see what the role of linearity is in that. So the kind of primitives that you have in these languages are, for example, this make channel function that you call with a specification of the protocol of the communication that's going to occur on this channel. So in this case, it's a very simple protocol. We're just going to receive a single natural number. And then we get two channel endpoint references with dual types. One expects to receive, and the other one expects to send. Now we can hand one of these endpoints, in this case the receiving endpoint, to a foregraph thread. And when we receive, we get a new endpoint reference. And this endpoint reference has a different type, kind of representing that the protocol has progressed. The other endpoint we keep on the main thread, and then we can send on it, and thus communication occurs. For this to be type safe, it is absolutely crucial that that you treat these references as linear. You can imagine that if you were to use one endpoint twice, and you have some buffer maybe at runtime that represents the state of this channel, then one of these threads might race to get a value, and the other one will be stuck waiting for a value to appear in this buffer, and it will never happen. And the other thing that we cannot do is forget about these reference endpoints, because similarly, a thread will get stuck somewhere. So how is this enforced in the type system? Well, first of all, we have these restrictions on the context to the relevant part, and that allows us to check that everything is used in the end. And the other thing is for binary expressions, you have these witnesses of the fact that a context is split disjointly over, in this case, sub-values. And it's also these witnesses that are kind of in the way of scaling this up and getting these nice, concise specifications, because that means that we're going to be handling these proof terms, because that's what they are, explicitly, and we have to construct those, and we have to manipulate those. How bad does this get? Well, this is kind of the signature that we want to write for an evaluation function for a session-type language, where the channels you can think of as the buffers containing the state for these channels. And this is what we have to write to maintain linearity. And what we've done is we've annotated everything that is a value or contains values with these phi's, which denote their use of the channel, available channel endpoints. And then we have these additional witnesses, again, for the separation of the uses, ensuring that nothing is used twice. And then in addition, we also have these inclusion facts, which are part of the state invariant, which means that every reference that is floating around can actually be dereferenced in the state that we have. Okay, so this is clearly not what we want. We have this problem that type safety depends on linearity, and we can kind of witness linearity by maintaining separation, but it causes all of these proof terms in these interpreters, kind of spoiling the nice approach. So the solution that we propose is to use a shallow embedding of a separation logic, a proof relevant separation logic, as we call it, in Agda to clean up these definitions again. And I'll give you a taste of how that works. So going back to these typing rules, the way that we're going to embed them into Agda is to think of values as predicates over a resource, namely these phi's, these session contexts. And then we write these kind of types where we use the type formers of predicates to combine them. So in this case, for a channel reference, we just witnessed that the session context is a singleton containing a single element of type channel alpha, matching the kind of this fact in the typing rule. And for n-ary expressions, we combine things using the separating conjunction, hiding this separation witness. Now the thing to note is that we've kind of gotten rid of the name of the channel. This is again a nameless representation of syntax, just like the Brown. But that also means that if we actually want to dereference one of these references, we have to look at the separation proofs, which is why we chose the name proof relevant separation logic for the flavor that we implement. Okay, so let's go back to this ugly signature that we had before. And I think it should now be clear that we can get rid of these things using the separating conjunction. It's not so clear how we're going to get rid of these inclusion proofs, which are part of the invariant of state. And that's actually another contribution of this paper, is that you can fold this into your notion of separation, or you can enrich an arbitrary notion of separation with these notions of supply and demand. And the result is, again, a separation algebra for which you get this separation logic. It also gives you these modalities that kind of distinguish the role of channels as the supplier of state and things that are value-like as users of state. Okay, so it's really nice. I should note that this is the separation logic's magic wand, which allows you to abstract over resourceful values. Right, so it's nice that we can get these nice types for our evaluation functions, but we also have to implement them. And the way that we approach this is we kind of take a monad as a separation, as a abstraction boundary, and we can kind of poke through our abstractions when we implement the actions in the monad, but we want to be able to combine these actions in a nice way to get nice interpreters. So what we do is we kind of construct these linear counterparts of the monads that we're familiar with. So here, the latter part of the signature, the channels to updated channels and the value, we view as a state monad. Right, and what's important here is that such a monad not just encapsulates the computational part of this effect, but it also is able to hide the bookkeeping that goes with this effect. So in this case, that notion of inclusion that you need is completely encapsulated in this monad. And you can see this in the interface because none of these things use the modalities for supply and demand. And that means that the clients of this monad really are only aware of adding up demand in a disjoint fashion. They're unaware of how the state monad ensures that everything can be dereferenced in the state that it's carrying. Right. The other important ingredient is that these monads are strong, in this case over the star of separation logic. And that enables us to program with these monads in Agda, which is kind of surprising because working with these bonds is notoriously difficult, which is maybe why a lot of people use tactical languages for manipulating separation logic propositions. And the resulting interpreters kind of look remarkably unremarkable, which is kind of our target because we want this. We want to give this feeling to our users that they're getting this type safety proof for free. So how does it work? We pattern match, in this case, on a linear function application, and we get this separation witness that separates the typing context. Then we evaluate the function expression with a twist that we have to specify on which part of the environment we are going to compute. And for that, we use the frame operation of the linear reader monad in which we're in. Now what we get is a closure. We have all the benefits of these intrinsically typed interpreters, so Agda knows that we're going to get a closure. And what's left is exactly the part of the environment that we need to interpret the argument expression. And Agda is also able to see this. At the same time, we have to use monadic strength to get a witness, sigma 2 here, that the value that we computed is disjoint from the environment that we computed earlier. And using that witness, we then construct the environment for the body of the closure, which we finally interpret. And again, Agda is able to see that the environment that we've constructed is of the right type for the body. We think this is really neat, and it really satisfies all of the requirements that we've outlined. Yeah. Now, that's everything I wanted to show you in this talk. In the paper, you will also find the construction of these proof-relevant separation algebras, over which we define this separation logic, and several instances of these PRSAs, the ones that I've used, the ones for context separation. But for the session-type language, you have a more fine-grained notion of separation to also be able to split these channels into their two endpoints. Then we have an instance that enriches a arbitrary PRSA with these notions of supply and demand. And I think we have a couple of more instances. And then we construct these monads, the reader and state monad that I've used in this talk, but also the free monads, which we use to deal with concurrency in the session-type language. And of course, we have a complete semantics for the case studies that we do, which also includes a lambda calculus with strong references, which is also where you need this maintain linearity. And of course, you can find our entire artifact online. Thank you for your attention.
Questions?
Thank you for your talk. Could you explain how you deal with a termination checker in Agda? I mean, potentially it's good that you have like intrinsically typed syntax, right? But even for simply typed lambda calculus, it's not sort of completely trivial to write an interpreter. We know that it terminates, but it requires some proving. I don't know how Agda goes about it, so I try this in Coq.
You're completely right. It's a little bit of an orthogonal issue, and so I haven't. So what we do in the artifact is we either use a delay monad, a sized delay monad to deal with termination. That doesn't work for the session type language, where you kind of wrap up threads and put them somewhere and then execute them somewhere else in a scheduler. So there we use fuel.
Thank you.
More questions? Okay, so I have a question. So did you ever try to use this formal language to write a bunch of examples to see how easy it is to...
I have exactly one example
okay.
That's in the repository. not just interprets or runs in the Agda mode where you interpret it, but it also compiles and then you can run it, which is the wise thing to do because it takes a while otherwise. And that works. I mean, I've annotated with debug.trace to get some useful output from there, and that seems to do what it should be doing.
Do you have a plan to provide more examples?
No. So, I mean, writing these manually type-checked terms is quite hard. Already when you have the Brown encoding, but when you do code Brown encoding, which is what this was, it's actually less human consumable. So what we hope is that you normally would write a type checker that produces the terms from a raw syntax, and then it would be more feasible to create a body of examples.
So you are considering design a surface language that omit some of these annotations?
That would usually be the approach, yeah.
Okay, great. Any more questions? All right, so let's thank the speaker again.